All right, welcome back to Probability and Measure. We are on lecture number 3 now. We have learned what a measure is. We've learned that we can extend a free measure to a proper measure. The question now that we have to answer is that extension unique? Or could I extend to lots of different measures? We're going to prove uniqueness in today's class. We're going to use a tool called the Dynkin pi lambda theorem. There are different ways to get to uniqueness. This is the one we're going to use, and this theorem will not just be useful for uniqueness, but it'll be useful for proving some other things about Lebesgue measure. So let's get into the lecture and find out what this is all about. Welcome back to another lecture of Statistics 571, Probability and Measure. Today we're going to follow up from our last lecture. Our last lecture was on the Carathéodory extension theorem, the idea being that if I have a measure on a ring or a field, I can extend it to an entire sigma field. Now, the question that hasn't been answered yet is that extension unique? That is, I know that an extension exists. Are there other extensions that are different, or is every extension the same thing? So that's what we have to discuss today. We want to prove uniqueness. The answer is that yes, it is unique, but we have to show that mathematically, and there's going to be some little tricks that we're going to need to do that, which are going to come back later as well. That is, specifically, we're going to use the approach by Dynkin, the so-called pi lambda theorem. Now, this is going to be a very useful tool in this context for proving uniqueness, but it's also going to be a very useful tool later when we can use the idea of pi systems and lambda systems to, well, prove new things about probability measures and I guess just general measures measures in general, I should say. General measures in general, because that's not redundant. Anyway, let's get into the notes and see what we have to do. So, as I mentioned, there is a big question. The question is simply that if I have two measures, mu1 and mu2, and they're going to be on a sigma field generated by A, kind of a terrible script A, but that's okay, where script A could be a field, for example, then the question is if mu1 of A, this is regular capital A, is equal to mu2 of A, this is for all A, in A, script A, which, then the question is, does mu1 of B equal mu2 of B for all sets B in the sigma field generated by that collection of sets A? Right? We want the answer to be yes. That's what we're going to try to prove today. And what we need two different additional definitions to move forward with this. Now, there are different ways to approach this proof, and I think in certain textbooks they don't take this approach. I just personally like this approach, so that's what we're going to do in this class. So we need two definitions. The first definition is going to be for something called a pi, I'll just use the Greek letter, a pi system. So a pi system is basically, well, we'll say a collection of sets. A is a pi system if for any A and B in A, then A intersect B is in A. And that's it. It basically says if I have two sets in my pi system, then I necessarily have the intersection of those two sets also in the pi system. Now, this pi system is actually a very natural place to start when you're thinking about probability. Because if you think of A as some possible events and B as some other possible events, what we're saying is the intersection, the and, A and B is also a possibility, which is basically saying that, yeah, if A can occur and if B can occur, then I can also consider A and B both occurring. And that's all we have for the pi system. It's a pretty simple setup, which is nice because we're going to use it below. But we also need another type of thing, and this other thing is going to be called a lambda system. So the lambda system is, well, a little bit more complicated. We'll say a collection of sets. We'll use script L is a lambda system if, oh, I forgot one thing for the pi system. Let me put that in here. Also, the null set is in every pi system. So the pi system has to contain intersections. It also has to contain the null set, just as a little extra thing. So for the lambda system now, we need, well, the entire space, omega, is going to be in the lambda system. So it contains, I guess, the whole space as one of its elements. Also, for A and B in the lambda system, well, I guess it's in L. This is the conditions that make it a lambda system, such that A is contained in B, then B set minus A is also in the lambda system. So what that means that, again, if I have nested sets, A and then B outside of it, I can, well, subtract A from B, and I can, that set is also in the lambda system. Well, again, much like the fields and the rings and the sigma fields, we're just defining which sets are going to be in our collection, right? That, in this case, make it a lambda system. So lastly, if we have a countable collection of sets A, I from 1 to infinity, we'll say we'll just index them this way to emphasize that we have a countable set that is pairwise disjoint. Then, and all the A's, I's, I guess I should be precise, and the AI are in the lambda system. Then, necessarily, we also have that the union, the infinite union, the infinite countable union, I from 1 to infinity, of AI is also in the lambda system. So, what we have is we have what? We have the whole space. We have the ability to do set, I guess, subtraction, if they're nested. And we can, well, do pairwise disjoint countable unions. Cool. So the lambda system is actually very similar to a sigma field, except that it's closed under countable disjoint unions. So basically, without this, we have a sigma field. So we can only take unions when they're disjoint in the case of the lambda system. Yeah, and then we have a couple other things to note. One other note I wanted to point out, which is that the pi system is a very general note. A field is a pi system. That is, if I have a field of sets. It's a collection that contains all intersections and also contains the empty set, or the null set. So yes, in that case, a field is also a pi system. This will be important because we're now going to state the big theorem that we want to prove. And the big theorem, which is uniqueness of extension, and what the theorem says is that, well, it's basically what I started with at the top of this lecture. Let mu1 and mu2 be sigma finite measures. This is important. We need sigma finite measures. Recall that sigma finiteness means that we can cover the entire space, omega, by a countable collection of sets that all have finite measure. So for example, the real line, I can cover the entire real line by intervals n to n plus 1, and those are all going to have, let's say, Lebesgue measure a length of 1. There are cases where you can't do that. Things get kind of bad. So we're going to stick with sigma finite measures mostly. In the probability case, we have finite measures because the entire space has a measure of 1. Something has to occur, right, with probability 1. So yeah, basically we need to have sigma finite measures here. Be sigma finite measures on, we'll say sigma of script A. So again, the sigma field generated by script A, where script A, that's a terrible, I have to work on my script A's. By the end of this course, I'm going to get it down. Anyway, script A is a pi system. So again, we're using the pi system to generate the sigma field. Then, if mu1 of not A, capital A, not script A, is equal to mu2 of A for all A in the pi system A, then mu1 and mu2 are equal to each other on the entire sigma field. So that's pretty cool, because it basically means that if we start with a, well, even like a nice collection of sets, like a pi system, then we can, when we extend our measures to an entire sigma field, there's only one answer that we're going to get out. There's only one measure that we're going to get out, and that's good, right? Because otherwise, we could run into some trouble. Now, how are we going to prove this? Well, we're not going to prove it right now. First, we're going to state another theorem, which is Dinkin's pi lambda theorem, and we're going to use that to prove uniqueness. So we're going to hold this off for a second, right? This is our long-term goal for this lecture. But first, what we need is another theorem. And this is the Dinkin pi lambda theorem. I actually don't know who Dinkin is. Probably look that up. Because I've only ever heard of the name occurring specifically for this theorem, but it's super useful when you're dealing with measure theory and probability, so probably a smart guy. All right, so what do I have? Let A, script A, be a pi system. And script L, well, be a lambda system. And A, the pi system, is contained inside the lambda system. Then, necessarily, the sigma field generated by the pi system A has to be contained within the lambda system. So that's kind of neat because, right, the pi system could be pretty simple. It's just sets and all of their intersections and the empty set. When we generate a sigma field from that, we're taking all these countable unions and things like that, so it really blows up, right? We get a lot more sets in the sigma field. But it turns out that if the pi system is in this lambda system, then the entire sigma field generated by that is also in the lambda system. So in some sense, this lambda system has to be pretty big, is what we're getting at. Now, how do we prove that? Well, the proof isn't too bad. So, first, we're going to say let script L naught be the smallest lambda system such that script A, the pi system that I started with, is contained within this lambda system. So this is just the smallest, right? We can imagine that such a thing exists. So then, of course, since L naught is the smallest lambda system containing A, it has to be contained within L, the lambda system that was in the statement of the theorem, right? Because it's just the statement of the theorem is I have some lambda system. This is L naught, the smallest lambda system, so it has to be contained in any other lambda system that, well, contains A. So the goal of this is to show that L naught is also a pi system and a collection of sets that is both a pi system and a lambda system is a sigma field, which I think I'm leaving in my notes as an exercise. Yeah, I think I just put that in as an exercise. You can check it yourself. It's really not the most exciting thing to do, right? If you want to show that something is a sigma field, you just have to show all of the pieces of the sigma field, things like countable unions and intersections already done, right? So it's nothing that profound. You just have to check all of the little boxes to show that it is in fact a sigma field. Nevertheless, that's what we're going for here. So the goal is to show that this L naught is also a pi system. If it's also a pi system, it's a sigma field. And if it's a sigma field, it must then contain... let me follow this logic here. Then we, I guess, necessarily have that the sigma field generated by A, remember that's the smallest sigma field that contains A, so this would necessarily have to be contained within L naught, and that's contained within L. So that's what we want to do. And all it comes down to is showing that L naught is a sigma field. Well, showing that L naught is a pi system. So this goal basically gets reduced to show that L naught is closed under intersections. So this is kind of neat in the sense that we've taken this more abstract proof idea, right, where we're saying, okay, well, how in the world do we show that L is going to contain the entire sigma field. And it turns out that all we really need to do is show that this L naught is closed under intersections. And then we're done, based on this little mini paragraph I wrote here. So how do we do that? Well, let's do that now. Okay, so first, let L prime be all of the sets B in L naught such that B intersect A is also in L naught, and this is for all A in script A, the pi system. Okay, so what's that basically? Basically, we're saying we're going to take all of the B's in L naught so that if I intersect them with any element of A, script A, I get an element that's within my L naught, the smallest lambda system. So what is that? What do we know about L prime? Well, then we know that A is contained in L prime. Wait, not L prime. Why? Well, as A, script A now is a pi system. So, right, it contains intersections. So, well, I know that, wait, I want an element. A is a set that is inside L prime. And this is, oh, no, wait, I did have it the right way. Sorry, my A's and my script A's are getting all messed up. What I meant to say is that script A is contained within L prime. Because it's a pi system, so any element of that can be intersected with another element of that and still be within it, because pi systems let me do intersections, right? So that's all there is to that bit. So now we want to... So now let's show that L prime is also a lambda system. So first of all, well, omega is the entire space, is an element of L prime. This is because A is contained within L naught, right? And now we have two more things, and we're going to have a couple, well, it gets a little bit tricky here, so let's try to proceed slowly. We have if B1 and B2 are in L prime, such that B1 is contained in B2, then we have for any A in script A, we have that B1 intersected with A and B2 intersected with A are both elements of L naught. Right, let's think about that for a second. Right, what we have is we have B1 and B2 are both elements of this L prime. We didn't use the nesting, that's going to be the next thing. But what we're saying is that if we intersect them with A, oh that's right, because they're in L prime, we can intersect with A and they're going to be within L naught. That's the definition of the collection of sets L prime. Right. But more interestingly, thus what we can do is we can say that B B2 intersect A minus B1 intersect A, right? These are still going to be nested, is going to be B2 minus B1 intersected with A. And this is also going to be an element of L0. Therefore, B2 minus B1 is an element of L prime. So what we're doing is we're just checking that first result, one of the conditions of the one of the requirements of being a lambda system, that is specifically this second bullet point here that tells us that, well, if I have nested sets, then I can do a set subtraction. And that's all we did down here. Now note how we did that, right? We did that by intersecting with A. The idea is that we don't know a priori if we can just do a set subtraction, but what we can do is we can intersect with A, move into L0, which is a lambda system, then we are allowed to do set subtractions, and then as a result of the definition of L prime, we find out that we can also do set subtractions in L prime. So that's the trick, right? The trick is to kind of use A to push ourselves into a place where we know what we're doing, and then we can pop back out to L prime. I always kind of find these proofs amusing. Anyway, what's the next bullet point? All right, so then the next and final bullet point is going to be to check the final condition of the, well, that we need to have a lambda system. So that's if we have a countable collection, Bi, where I is going from 1 to infinity, and these are all elements of L prime. I guess precisely this sequence is not an element of L prime, but each individual element in the sequence, each Bi is in L prime. But we'll just use that shorthand, even if it's slightly imprecise, and we'll say, and these are pairwise disjoint. Okay, so what we want, right, is we want the union of these things to be in L prime. We don't know if that's true. We have to figure it out. So we'll say then, for all, or any, I feel like for all and for any are kind of the same thing, but we'll say for any A in the pi system, script A, we have that B, where am I? Ah, there it is. A intersect Bi, I is in L0. This is the definition again of L being in L prime, means I can take an intersection with an A and get to L0. Thus, or therefore, what we have is that the union I from 1 to infinity of the A intersect Bi is, well, also in L0, and this can be written as A intersect the union I from 1 to infinity of the Bi, and these are in L0. Hence, the union I from 1 to infinity of the Bi's is going to be in L prime. So again, we did the exact same thing twice, which is we wanted to check a condition of the lambda system for L prime. We did that by pushing ourselves into L0, where we have a lambda system, and we can do set subtractions or countable disjoint unions. And then once we're done there, we push ourselves back up to L prime to show that L prime is also a lambda system. Now, by, I said by definition, maybe by construction, by definition, or by the, I guess, how we defined L prime, we have that L prime is going to necessarily be a subset of L naught, right? What is L prime? L prime is just all the sets in L naught, well, such that this condition holds. So to be an L prime, you have to be an L naught, right? That's just a requirement based on how we constructed L prime. But I guess I should say less than, or not less than, but contains or possibly equal to. Because what we know is that but L naught is minimal. It's the minimal lambda system that contains A. And since we just showed that L prime is also a lambda system and also contains A, it turns out that L naught is actually equal to L prime. They're the same thing. Cool. Therefore, L naught contains all intersections with elements of A, script A. So we're almost there. We haven't quite solved this yet. What we've shown is, we wanted to show, right, that what we have is we can remember that L naught, where were we? The goal is to show that L naught is also a pi system. So I can take any two sets in L naught, intersect them, I'm still in L naught. We haven't quite gotten there. What I said is I can take any set in L naught, intersect it with a A, and I'm still in there. But I don't know if I can take any two arbitrary elements of L naught and intersect them and still remain within L naught. To do that, I know this is going to annoy people with notation, but we need one more step. So lastly, let L double prime, you know, be all of the B's, all sets B in L naught, such that B intersect C is an element of L naught. And this is for all C in L naught. Okay. How's that any different from what L prime was? L prime says I can intersect an L naught set with an A set and stay in L naught. Double prime says I can take an L naught set and intersect it with another L naught set and still be in L naught. So these are all the sets, these are all the elements of L naught that I'm allowed to do intersections with. The goal is to show it's the entire thing, which is I can do intersections with any element of L naught, right? That's what we wanted to show. So since L naught is equal to L prime from above, this implies that A is contained, the pi system is contained within L double prime. Right? And then if we use the exact same arguments as we did for L prime, basically, then do the same thing we did to L prime to L double prime to show that L double prime is a lambda system. And thus, L double prime is equal to L naught, just by the exact same argument we did above. And then we're done, because therefore L naught contains, or is closed, I guess, under intersection. To be a little bit more precise, intersections, therefore L naught is a sigma field. Therefore, the sigma field generated by A is necessarily contained within L naught, and we said before this has to be contained within L, and we're done. Hooray. What did we just prove, right? When you get to the end of these, sometimes it's like, what in the world did we just prove? Let's get the QED box in there. I love the QED box. Always makes me happy to put one of those in, right? What did we show? We showed that if we have a pi system, and if we have a lambda system, and if the pi system is in the lambda system, then the sigma field generated by the pi system is also in the lambda system. Good stuff. We're going to use this to prove uniqueness, the big blue theorem here. So that's the next thing we're going to do, is we're going to jump right into this proof. And in fact, we're not just going to do it once, we're going to do it twice. I have two different proofs here. The first one is for finite measures because it's a little bit easier, and since this is a probability and measure course, it seemed natural to let's do that because probability measures are finite measures. But we can also do this for sigma finite measures, so we could always extend it and make it a little bit more general. The main idea is that there's to show you how we can prove a simpler version of a theorem and also prove a slightly more complex version of the same theorem, or a more general version of the same theorem. Because, right, it's kind of the journey, not so much the destination. We're going to get that theorem. It's always good to prove a theorem, but also seeing how we prove the theorem is going to be useful. Now, most of the theorems we're proving in this course are basically check a whole bunch of stuff. Does it satisfy the conditions of a sigma field? Does it satisfy the conditions of a lambda system, etc., etc.? But nevertheless, it's good to see how these all work. So we'll say proof of uniqueness, and this is going to be for finite measures. Okay, so first, because it's a finite measure, we're assuming that mu1 of omega is equal to mu2 of omega, and that these are finite. Maybe we should read the theorem again, just to make sure we remember what we're actually doing. Right? The theorem says that if my two measures agree on A, the pi system, then they must necessarily agree on the sigma field generated by the pi system. So what we're starting with is, okay, we just have finite measures. This is going to allow us to basically do some subtractions with omega. Now, so this is going to be the first little bullet point. The second bullet point is going to be now let L, well, what do you think it's going to be? It's going to be a lambda system, but we don't know that yet. I know that because, well, I read the proof and wrote it all down. But right now, L is just a collection of sets, B. Subsets of omega, such that the measure mu1 of B is going to equal mu2 of B. Right? So this is just saying L is all the sets where the measures coincide. We want to show that this is a lambda system and then be done, right? If L is a, not L, lambda system, we're done. Why is that the case? It's the case because, of course, A, the pi system that we're starting with, has to be contained within L, because we know that the measures coincide on A, and L is all the sets where the measures coincide. So L has to contain A. And from Dynkin pi lambda, what that means is that the sigma field generated here also has to be contained within L. And we're done, because that means that the measures coincide on the entire sigma field, and that's what we wanted to show. Now, how do we show that this thing is a lambda system? Well, we just got to check the conditions again. So first, so now we've reduced the proof. The new proof, right, has been reduced to show that L is a lambda system. Well, how do we do that? The first thing is to note that, well, the entire set is in L. This is by assumption. This is where I said we can kind of make things easier by assuming that we have a finite measure and that the measures coincide. They give us the same measure, the same value for the entire space, omega. Which, again, in a probability sense is always going to be true, because every probability measure is going to give you a probability of 1 for the entire space. Now, next, if, let's say, A and B are both in L with A contained in B, nested within it, then, well, what happens? Well, then we have that the measure mu1 of B minus A, right? We want to show that this is equal to the measure mu2 of B minus A, because then B minus A will be in L, and this is a condition for the lambda system to be a lambda system. Well, what we're going to do is we're going to do this. We're going to say mu1 of B minus A plus mu1 of A. Okay, so what's that equal to? Well, that's just equal to mu1 of B. Measures are countably additive. B minus A and A are disjoint. So, right, we can just add them together, basically, and get B. Now, because B is in L, it has to coincide, the measures coincide on B. So we can swap to mu2, right? We swapped from mu1 to mu2, and then we can push ourselves back to what we had before, but with mu2. And now we have the same thing, but with mu2, and everything here has to be finite, thanks to our assumption, right? Hence, B minus A is in L. Because I can subtract mu1A from mu2 of A, they're the same thing because A is also in L, and that implies that the measures coincide on B minus A, which means B minus A is in L. Cool. Again, the finiteness is kind of an important assumption to make this work. Otherwise, I couldn't just subtract, right? So there's some little tricks here, right? If we don't know a priori that the measures are going to be finite, I might not be allowed to just subtract one side from the other. That might not make sense. So these are all these little tricks to be careful of if you're trying to prove something, right? That's why I'm starting with this simpler setting. Now we're just going to check the next thing for the lambda system, which is that if ai, I from 1 to infinity, are pairwise disjoint, And of course, AI is in L. I'll write it the correct way this time. So then what we want to show is we want to show the union is also in L, which means we want to show that the measure mu1 of the union, I from 1 to infinity, of the AIs, we want this to equal mu2 of that union. Every time I say Mewtwo, I can't help but think of the old Pokemon game from the 90s. Not sure if anyone ever played that, but I assume that the character of Mewtwo is still around in like the 10th or 12th or whatever iteration they're at these days, but never mind. It just keeps popping into my head, so had to get it out there. Anyway, right, we have AIs or pairwise disjoint, which means we can use countable additivity and write this as a countable. We can write this as a countable sum over each of these. Now the measures coincide for each of these AIs, so we can switch from mu1 back to mu2. And then we can just cram it all back together because mu2 is also going to be countably additive. And the AIs are still disjoint, so that's all there is to it. And this is, again, finite. Cool. Yeah, so that's basically it. Therefore, right, the countable disjoint union of the AIs is also within L. And we take all of these three things, and this implies that L is a lambda system. Good stuff. It contains A, therefore L is a sigma field, and we're done, right? And A is contained in L. Therefore, we have L is a sigma field that contains sigma A. Actually, wait, it's not a sigma field. It doesn't have to be a sigma field, right? I think that's a typo in my notes, which I will have to change. Right, we don't care about L being a sigma field. We just want it to be a lambda system. If we go back to Dynkin pi lambda, right, the whole point of Dynkin pi lambda is not that L is just a lambda system, and if it contains A, then it contains the sigma field of A. Okay, so that's an error in my notes. I'll have to correct that before I upload them. Hopefully by the time you're watching this video, I've already corrected my notes, and yeah, we don't want this. L is not a sigma field. That's not what we want. Basically, the point is that the sigma field is also contained in L, and L, anything in L has to is where the measures coincide, which means the measures coincide on all of sigma A. It's equal to mu2 for all sets in sigma A. There we go. That's what we wanted to prove. It doesn't need to be a sigma field. It just needs to contain the sigma field, and then we're done. Right, so that was kind of the easier version of the proof. The point is that everything's finite, so I can do things like subtract. If things are not finite, we have to try be a little bit more clever. So let's do another proof. Proof of unique... Oh, I forgot my QED box. QED. I love that. Most of the courses I've taught so far don't actually have proofs in them, so it always feels good to finish a proof with a QED box. All right, now we're going to do sigma finite measures. And then we can also compare kind of how these, well, compare and contrast, right? So, for any A in A such that mu A is equal to mu 2A and finite, we define L sub A to be all the B's that are subsets of omega, such that mu1 of A intersect B is equal to mu2 A intersect B. Now we'll say proceeding as in the proof for finite measures, we can show, I'm not going to do it, but we can show, the mathematician's way of saying, I really don't want to have to write this all out again, but you can do that at home if you really want to. We can show that LA is, well, what do you think it's going to be by my notation? A lambda system. Hurrah. And therefore, sigma A, not A, sigma script A is contained in L sub A by Dynkin pi lambda. So, okay, that's kind of a hand wave, but more or less we're doing the exact same thing as the previous proof. But what we did was we found an A that has a finite measure and we intersect everything with it. So we basically took our sigma finite measure and we pushed it into the state where it becomes finite by having to intersect everything with A. And then we can just do the exact same argument I did above. That doesn't prove the theorem. That just gets us, well, part of the way there. So this is step one. Maybe I'll just put a little green bullet point here. The next bit we have to do is by sigma finiteness, I guess that's a word, we decompose omega as a union I from 1 to infinity, a countable union, right? Because sigma finiteness means I can have a countable union of AIs for AI in A, and the measure mu1 of A, of course, equal to the measure mu2 of A, and finite. So there's the trick, right? Which is, if I take any set with finite measure, I can just intersect everything with it, and I can, well, get the result I want. Now what I'm going to do is I'm going to take sigma, which may have infinite, which in this case we're kind of assuming will have an infinite measure, and I'm going to cut it up into a bunch of finite measure pieces, a countably infinite number of finite measure pieces. Okay, thus, what can we do here? Well, this means for any B in the sigma field generated by A, and any N, just a natural number, we can get that mu1 of the union. Now, it's not going to be an infinite union. It's going to be a union of the first n B intersect AIs. Well, this we're going to kind of do is something similar to before. In this case, we can use the... did I write that this is... Oh, yes, we're going to use inclusion. Okay, so they're not necessarily disjoint. We're going to use inclusion-exclusion. I want to double check that. So these are not necessarily disjoint as we had before. They're just, the AIs just cover all of omega. But what we can do is we can rewrite this using the inclusion-exclusion formula, which is going to be a little bit messy, but it's going to look something like this. I from 1 to n of mu1, b intersect AI. And then we're going to subtract all of the I less than j of mu1 b intersect AI intersect aj. Then we're going to add the triple ones and subtract and so on. So this is ... use inclusion exclusion formula. Right, it's messy, but it would just extend into, it's all finite in some sense. We only have n elements, so we're just considering all the possible ways to like chop them all up and add and subtract so that these two sides are equal. So this also works for mu2, of course, because it's also just a measure. So since A is a pi system, AI intersect AJ is also an element of A, right? As well as further intersections. What that means, right, is that, well, AI is going to be in the pi system. The intersection of AI, AJ is going to be in this pi system. The intersection of AI, AJ, AK, AL, whatever, index, we're going to run out of letters, but the point is that no matter how many intersections I take of A's, I'm still going to be within the pi system. Therefore, mu1 of the union, I from 1 to n, of B intersect AI is going to coincide, is going to equal mu2. I from 1 to n, B intersect AI. Cool. And this is any n in the naturals. What I mean by that is finite. So for any finite n, we can show that these coincide. Great. So what we do is we now let n go to infinity and conclude. QED box. Right, so what did we do here? Well, this argument for this second version of the proof was just a little bit more complicated than the first. In some sense, we used the argument in the first part. The argument of the first part said, well, if everything's finite, then I just show that L is a lambda system and we're basically done. So we check everything, we're done. For the sigma finite bit, well, if I take a finite A and I intersect everything with it, then, well, I can show that that works, but that's not for all of omega, that's just for a single A. Now, I can cover omega with a bunch of A's, but I have a countably infinite number of them. So for each A, I can get a lambda system. What I want to show is that I can do this for, in some sense, all the A's, and that's what we do here. right? We basically go through this whole thing and show that, yep, these things can coincide for any number of these a's. If I take a to infinity, I basically show that it works on for any countable union here. Or no, it just works for b, sorry. The countable union goes away. If I union all of these together, I end up with just omega, right? And then I'm left with just b. So it means that the measures coincide for any b, where b at the top here is an element of the sigma field. Good stuff. All right, so that's the main point of today's lecture, but we know there's still a little bit of time for some bonus material. Yeah, so let's do that. So first we have a remark in the notes. The first one's on probability spaces and pi systems. So I think I already said this at the beginning of the lecture, but the point is that a pi system is very natural in probability theory. As intersection is kind of equivalent to and. Right, so I have an example in the notes. I don't really need to write it out, but I'm just saying that if we're rolling dice, right, we could ask questions like, is the sum equal to 8? We could ask, is the first value an even number? And then we can say, well, we can also and them together. We can intersect those events. So it's very natural to want to be able to intersect things when you're doing probability. What's really cool about the theorems that we proved today is that in some sense, that's all you need. You need a space of events, and you need to be able to and or intersect those events, sets of those events, those occurrences. And then we can extend that idea from that kind of simple setting into a, well, sigma field and a measure that makes sense on that. Oh yeah, maybe this next remark is kind of more interesting. The next remark is about sigma finiteness. Still not sure if that's a word, but we'll just go with it. Sigma finiteness, right? So we required sigma finiteness as a condition in this more general version of the proof. The sigma finiteness came in right here, right, where I can write omega as a countable union of AIs, all with finite measure. If I can't do that, this proof breaks. And we have an easy counterexample to show that it doesn't work for, I guess, whatever non-sigma finite measures. That is, we can have non-unique extensions. So let's work through this one, actually. I think I found this, if I recall, in Dudley's book. He has or I'll have to remember where I found this, but he's got a lot of kind of like clever little counter examples hidden within the text. So I think that's where I got this one. I shouldn't say sigma, I should say without. Then uniqueness fails, may fail. I'm not going to, bet my life on it never working, but I'm going to assume that in many cases, if not all cases, where you don't have sigma finiteness, this will fail. At least we have one counterexample to show that we can't generalize this theorem any further, which is always a good thing to know. Otherwise, we could spend our days fruitlessly trying to prove something that is not true. Anyway, let's take omega to be the unit interval, half open, half closed, just because it makes everything a little bit easier, except for LaTeXing. It's super annoying for LaTeXing, but besides that, it makes all the math easier. Let's let A be the all finite unions of half-open intervals. Those are of the form A, B, where A is going to be greater than or equal to 0, and B is less than or equal to 1. And now we're going to define mu is a set function that assigns 0 to the empty set. Well, that's good. And infinity to any non-empty set. So kind of a dumb function, to be honest, but that's okay, right? We're just using this as a counterexample to the idea that we require sigma finiteness. So it basically says if I have an empty set, I get 0, and if it has anything in it, if the set has anything in it, then I get infinity. Cool. So the idea is that in this case, yeah. So therefore, the outer measure, sigma star, assigns infinity to any subset. Remember, the outer measure is a function on the entire power set. So I could take any subset of omega, plug it in there. It's going to assign infinity to any subset of omega that is not the empty set. Okay. But we also have this idea of the counting measure. The counting measure is basically it counts the number of elements in a set. So what's it going to do? Well, it's this also assigns 0 to the empty set and infinity to any AB interval or finite number of finite union of half-open intervals, because if you have a half-open interval, it's going to contain a continuum of points, which means it contains an infinite number of points. If I count that, I count to infinity. However, it'll assign, for example, it'll take, I didn't give the counting measure of like a thing like mu. It'll take something like 1/4, 1/2, and 3/4 and assign it a value of 3 because it has 3 points in it. Oh, I shouldn't say this is not the counter, this is the outer. Yeah, and this does not coincide with mu star. So again, kind of a silly example, right? Because we have a function that's going to give me infinity for anything that's not empty, but the point is that this is an example of where you would require sigma finiteness. When you don't have sigma finiteness, you can run into trouble like this. Right, so there's one other little section I wanted to talk about before we end this video lecture, and that's the idea of completeness. Now, I'm not going to go into the proofs and theorems regarding completeness. I just want to talk about it kind of in a more general setting, and if you really want, you can look up, I think, Chapter 3 in Dudley's book, Real Analysis and Probability, and he'll have more formalisms here. So the idea is that we want to complete a measure. What in the world does that mean? That is, if E and A only differ on a set of measure 0, then we want both E and A to be measurable and have the same measure. You can think of this like if I was taking Lebesgue measure, the length of an interval, for example. If I have an interval, and then I have that interval and I take out a single point, it should still have the same measure because that single point is not going to change anything. It's like an infinitesimal. So that's the idea in a nutshell. So what we need is we need a quick definition, something called the symmetric difference. I don't think I introduced this before, but, well, if I did, I'll just introduce it again. It's a set operation. For sets A and B, the symmetric difference, which is often written I guess, delta or triangle B as an operator, and this is going to be A minus B unioned with B minus A. So it's basically, I have to be in one of them, but not in both of them. This is the XOR operation, if you like computer science, right? Basically, let's Venn diagram this thing because, right, if B is in blue, or B is green, of course, it should be blue for B, but that's okay. A is blue, B is green. The symmetric difference is going to be the stuff that's in one, but not in the other. So most notably, the intersection of the two is removed. I think you can write it that way, actually, right? As the union minus the intersection, or as the... Wait, do I want the intersection of yeah. A minus B. I have it wrong in my notes. I wrote it right down here, but I have it wrong in my notes. I have A minus B intersect B minus A. That's another thing I need to fix. Hopefully by the time you're watching this, there will be no typos in the written notes. If you see a typo in the written notes, please let me know. Contact me, send me an email, leave a comment on the video, and I will try to fix that up. Anyway, this is the symmetric difference. Yeah, the intersection of that wouldn't make any sense at all. Right, so now that we have that definition, let's say for a measure space, which is going to be written, what notation am I? Oh, I'm using X this time. Okay, so we're using X. I don't know why I'm using X. I'll just stick with the notation I wrote down when I was typing up my notes. X, F, and mu. So our space X, our sigma field F, and our measure mu. With, of course, F, the sigma field, being a subset of the power set of X, the power set being all possible subsets. So, right, mu star, the outer measure, is going to be the inf of mu of A, and this is over all A that contain B. And of course, I guess I should write A in the sigma field F. Then the mu null sets are defined as the set or the collection n mu in the power set such that, maybe I'll do script n, such that mu star of n is equal to 0 for all n in script n mu. So the point here is that we have to use the outer measure mu star because a null set n may not be measurable, but it is going to be outer measurable. So that's why I use mu star here. Now, we say that a measure space is complete if this this null, mu null, the set, the collection of mu null sets is contained in the sigma field, F. Oh, and I think I had another little exercise here. Oh, yes. Exercise. Show that n mu is a ring. Which again is just go back to the definition of ring and check that everything holds for n mu. Not the most exciting thing, but you can still do it to make sure you understand the definition of a ring and how it works. So the idea is that we say that a measure space is complete if the sigma field contains all the possible sets of measure 0, or that have outer measure 0. And then, of course, they will have measure 0 if they have outer measure of 0, and if they're measurable. I love this course. Anyway, we can also talk about the completion. So if fx f mu is not complete, we can complete it. And basically what we do is by replacing f with, and then the notation here that I was using, which I think came from Dudley's book, if I recall. It's either Dudley or Billingsley's books. Those are my two primary sources for this theorems in this course. Yeah, the completion then... Yes, the completion here is going to be f v n, and what that's going to be is that's going to be all the possible sets A union n such that A is in the original sigma field F and n is in the null, a mu null set. Okay, and then there's a proposition in Dudley's book, which I'm not going to prove in this course, but I will state it very hand-wavily right here. It's proposition 332 in Dudley, which is Dud, L-E-Y. Yes. And this proposition says that basically this completion there we go, is equal to the set of B contained in X, all the sets B contained in X such that there exists an A in F, the original sigma field, such that A symmetric difference B is going to be in the null, a mu null set. And this is the smallest sigma field that contains both F and N. So what do we get at the end? Well, we end up with a new measure space, which is going to be X, F, V, N, mu, say, and we'll say mu bar, where mu bar of A union N is equal to mu of A, where again A is in F and N is a null set. So okay, it's not exactly the most interesting thing, but it allows us to kind of tweak what we have to make it work. The idea being that if we modify sets if we modify a set based on another set of measure 0, of outer measure 0, then we don't affect anything, and that's going to be important going forward. It's good to just be aware of that for both measure theory and for probability theory. But I think that's about it for today. So again, what did we do? Well, we proved uniqueness. We showed that if you want to extend a measure, you're going to get one answer, and that's good because that means now we have a way of, well, starting with a collection of sets that we're interested in and extending it to a bigger family of sets and showing that the measure on that big family of sets, one, that we can extend it, last lecture, and two, that that extension is in fact unique. There is only one way to extend it, and that's cool. We're going to do one more lecture on general measure theory before we get into the topic of integration. Next lecture is on the famous, the one and only Lebesgue measure on the real line, and the unit interval, because it's a little bit easier sometimes to work on the unit interval. We'll be doing that in the next lecture, so stay tuned for that, and see you next time.